Good day, learners. In this lesson, we will talk about motion along a straight line. Are you ready? Now let's begin. Let us first define what is a motion. Motion is a change in position of an object over time with respect to a certain reference point. So there is a change in a position considering time, and also there is a noticeable change in reference point. A very good example is being shown on the screen. We have there the red car. This vehicle is said to be moving along a straight road with respect to the tree. There is now a change in position, and we may see that the reference point over there is the tree on which the car is evidently moving because it is now far out from the tree. And that is only possible because this object moves over time with respect to a certain reference point. So, in general, that is motion. Moving on to the three key ideas to understand a motion along the straight line. Mind you that we are just talking this time a motion along a straight line. We may consider these three, which are the displacement, velocity, and acceleration. We will know them one by one as we discuss furthermore in the slides. Now, mind that a straight line is considered only as one dimension because on lesson 4, we will just talk about motion along a straight line, while in lesson 5, we will consider two dimensions of motion. Leading us in explaining distance versus displacement again, let us first define direction. When we say direction, you could still remember the definition of this one way back in our lesson in scalar and vectors. Now, again, direction in two-dimensional vector problems are often given in terms of the four cardinal directions, which are the north, the south, the east, and west. And in fact, you have solved many problems that includes these directions and even combined the two cardinal directions. For one-dimensional or linear problem, which is good and true in this particular lesson, we use the directions of the standard Cartesian coordinate system. Vectors to the right and up are positive, and vectors to the left and down are negative. You are very familiar with this one according to your general mathematics. Now, again, let us remember the difference between the distance versus displacement. When we say distance, it is only a scalar measurement of two interval between two locations measured along the actual path connecting to them, because there is no direction at all considered in distance. It is only good for the ground covered through time. While displacement is a vector, you have known that one already on the previous lesson. It is a vector because it is a measure of interval between two locations measured along the shortest path connecting to them, which also includes direction in this point. Now, the SI unit for displacement is meter. Do not forget that one since we are talking about path, since we are talking about distance, we're talking about direction. This one can be expressed through meters. So from this point forward, we will convert displacement into meter if it is necessary. The symbol used for displacement is this one, as shown on the screen. It is expressed in delta x and vector s. Moving on, we have here a very good example again to differentiate further about distance and direction. A cyclist travels around a 500-meter circular track 10 times. Question: what is the distance traveled and what is the cyclist's final displacement? I'd like you to answer it first. Now, there is a cue over there that the cyclist travels a distance of 500 meter each time she completes one lap. Since there are 10 laps as being emphasized in red font or in red color, her total distance is 5,000 meters. It is simply multiplying 500 meters to 10 times. Now, to find her displacement, we draw a line segment from the starting point to the end point of her motion. Because she starts and ends at the same point, therefore, her displacement has a magnitude of 0. This one is not new. This concept is not new to you as this has been discussed on the previous lessons. Moving on to the difference between the speed and velocity. I want you to become meticulous of this. Speed is only a scalar quantity, as that only refers to the distance traveled by a body in a given time. There could be time, but there is no direction for this particular quantity. So again, speed is just a scalar quantity. While compared to speed, velocity is a vector quantity. When we say vector quantity, that refers to the displacement of a body in a specified time interval. And since it is more particular on displacement, it talks about direction. Now, if a body moves through a displacement or delta x in a time interval or delta t, then its average velocity is or can be expressed through this formula. Average velocity is equal to the change in displacement or displacement over change in time. Again, that's average velocity is equal to displacement over change in time. Do not forget that the SI unit for speed and velocity is meter per second or m per s or m slash s. Do not forget its unit. It's very important as we have our solving. Speaking of solving, let us put the test into test your knowledge about speed and velocity. Let's have an example. Now imagine a ship sails 3 kilometers due west in 2 hours, followed by 5 kilometers due east in 3 hours. What is the ship's average speed? And what is the ship's average velocity? Now, if you are solving this one at home, you should use GRESA as, as you solve this problem. But for discussion's sake, we will just highlight the S and the A, which are the solution and answer. Now we have known on letter A that we are trying to get the average speed. Earlier in the definition, it was said that speed refers to the total distance in reference to time. With that so, it could be expressed in this formula. Total distance over total time. We have now the equation. Now, you simply put there, or you simply consider there, the values that can be substituted for each variable. For the total distance, there are two distances that are given on the problem, which are the 3 kilometers and 5 kilometers. And for the time, there is 2 hours and 3 hours. We just need to perform the operations, giving us 8 kilometer over 5 hour. Now, you just need again to do the operation. So 8 divided by 5, it will give you 1.6 kilometer per hour. But since we need to consider the value or the significant figures, we need to put it as 2 kilometer per hour, as there is only one significant figure, or the least significant figure on the problem is only 1. Now for letter B, what is the ship's average velocity? We are done with the speed. Now let's move on to the average velocity. I want you to remember that we assign negative value for the west since it goes to the left. So that's on the Cartesian plane. And for the positive, that's for the east. Now, time is not affected by direction, so it remains positive. So we have here, as presented earlier, the equation could be average velocity is equal to displacement over change in time. So if you will have that one and sum it up, we could put there negative 3 kilometers since it is due to west and positive 5 kilometers since it is due to east over what are the time? Well, you're correct. That's 2 hours plus 3 hours. You just need to perform the operations, giving us 2 kilometer per 5 hour. Now, what you will be doing is again perform the operations and it will give you 0.4 kilometer per hour. Now, since the final value is positive, we can say, well, going back again to the concept of vectors, we could say and associate it with the direction to be at the east. Therefore, the final answer for the average velocity is 0.4 kilometer per hour due to east or east. Wow, you're very good in solving this one. Now let us move on to the next concept, which is all about acceleration. Now, the acceleration is the change in velocity per unit time. And since we are talking about velocity, which includes displacement, it is a vector quantity. Now, an object is said to be accelerating if it is changing its speed, changing the direction of motion, or changes both the speed and the direction of motion. Therefore, we need to consider speed and direction of motion at this point. Now, remember that a negative acceleration in horizontal motion is an acceleration to the left, while because that is a negative acceleration, so it should be due or it should be to the left. If an object's initial velocity is to the left, the negative acceleration will cause it to speed up. If an object's initial velocity is to the right, the negative acceleration will cause it to slow down. So you can apply that one, the concept of that one again, through the x-axis in that Cartesian plane. It's very basic. Now let's move on. In able for us to express acceleration in quantity, we need to consider algebra. Algebraically speaking, we can express acceleration as acceleration is equal to change in velocity over change in time. Or if the initial velocity and final velocity are given, you may also express that one into acceleration is equal to final velocity deducted with initial velocity or minus initial velocity over change in time. Again, that's acceleration is equal to final velocity minus initial velocity over change in time. Remember, the SI unit for acceleration is a derived unit. That is, it is a unit created by dividing a velocity unit such as meter per second by a time unit such as s. Giving, but by the way, before I proceed, this concept has been discussed in lesson 1, the derived units, if you could still remember. Again, all of those will give us the units of units is equal to meter per second, which is equal to meter per second multiplied to 1 over s, cross multiplication, it will give you m over s squared or meter per second squared. So that is how it is. Now, let us put that one into a real scenario. Sir, I'm very excited to have that one in a real scenario. Now, here is the problem. When struck by a baseball bat, the ball's velocity changes from 15 meter per second west to 10 meter per second east in 0.30 seconds. Now, you need to determine the ball's acceleration. I want you to recall that in our standard coordinate system, we can represent west again as negative and east as positive, which we can highly use in our solution. Now let us determine what is the equation needed. Since we're trying to determine the acceleration, we will simply use the equation given as acceleration is equal to final velocity deducted or minus the initial velocity over change in time. Now remember that initial and final velocity on the problem is given. That is the reason why we are using this particular equation. Now, what should we do next? Simply, you will just substitute the values for each variable. So for the final velocity, we have there 10 meters per second, which is on a positive value, minus the initial velocity, which is 15 meter per second. Now, question, why is it negative? Yes, correct. It is because it's due to the west. And we can have that one in our coordinate system that west can be represented with a negative sign over change in time. So there's only one unit of time given over there, which is 0.30 seconds. So you could like simply put it over there. Now, operate all the if you will have all the operations computed, it will give you 25 meter per second over 0.3 seconds. Now, again, you need to do and perform the operations, giving you 83.33 meter per second squared, or if you will consider the smallest significant figure, we have there only 83 meter per second squared. So that would be your answer. Easy, right? It's really easy. Now let's have this one. How about putting and representing everything into a graph through graphical analysis? Now we have here the graphical analysis of linear motion. Sometimes it's better to understand things if there is a concrete representation of it. That's the reason why we have here the graphical analysis of linear motion. We just put over there the data into graph, enable for us to quantitatively and qualitatively express the data, and we will not have much confusion into it. Now, there are three main types of the graphs used in kinematics. The first one is the position time graphs. The second one is the velocity time graphs. And the third one is the acceleration time graphs. The relationships among these graphs provide us with some of our most powerful analytical tools because you could not express or you could not solve it right away by purely imagining it inside your or imagining it inside your head. You may try to express it in graphical analysis or in graphical representations, enable for you to solve it at its best. Now let's have the first type of graph used in kinematics, the position time graph. The graph shows the position time graph, or also called as the displacement time graph. For a ball rolling forward on a straight line, displacement is shown as d, or displacement with a unit of m, in this table. So as you can see over here, as time passes by from 0 to 1 to 2 to 3 and so on and so forth, what happens to its displacement? What happened? It is also improving, or it is also increasing, as its displacement from its origin is also increasing. So this is how position time graph is being represented. On the left, the displacement. Below on the x-axis is the time. Now, recall that let us express this one again, this particular graph, into a formula. Recall that the slope is equal to rise over run. Now, if you express that one in physics, it's actually meter is equal to displacement in meters over time. Or that is simply velocity is equal to delta x over t, or meter per second. The second one is the position time graph. Still the very first one graph, the position time graph. Now, if the slope of a position time graph gives velocity and uniform motion is constant velocity, then the graph must have a constant slope because both of them are increasing. In other words, if an object is undergoing uniform motion, its position time graph must be a straight line. Now, this time, let us represent it through this particular given. In this given, find the average velocity from time 0 up to time 5, or 5 second, from 0 second up to 5 second. Solution. At 0 second, we can see that the displacement is 0 meter if you will analyze the graph. Now, at 5 seconds, we could say that the displacement is now in 10 meters. Hence, we could solve that one through this. Velocity is equal to the final displacement over the initial displacement over change in time, which is 5 seconds minus 0 seconds. So if you will operate this operation, it will give you 2 meter per second. So that's simple. Now let us move on to the velocity time graph. In a velocity time graph, the slope of a tangent drawn to a point on a velocity time graph gives the instantaneous acceleration at that time. Now, we could say that in a velocity time graph, we can determine the instantaneous acceleration with the equation, as there are instant curve of a particular graph. Now, to express that one, it could still be expressed into actually acceleration is equal to velocity, or change in velocity over change in time. Still the same. What we are trying to emphasize on these graphs is just these data can be represented still through graphs or can be represented through numbers. It just depends upon the problem on how it is being given. Now, let us test your skill. I hope that you're now ready to answer and to solve it on your own, applying all the knowledge that you have learned on this particular topic. Let's test your skill. Now, here's the question. In 1980s, one of Asia's fastest running women was a Filipino athlete named Lydia De Vega. In the 100-meter dash event in Seoul, Korea, she attained a speed of 6 meter per second after 2 seconds from the start of the race. Now you need to solve the following problems using the given information. A. What is her average acceleration during the time interval? B. Suppose she attained a speed of 10 meter per second after 8 seconds from the start of the race. What is her average acceleration during the 2 to 8-second time interval? C. Suppose at 8 seconds from the start of the race, she slows down to speed of 7 meter per second for 2 seconds. What is her average acceleration for this time interval? Now, you are given the remaining time to solve for this particular problem. You need to upload this one. You need to send your solution on the chat box available on our MS Teams. Look at Lydia De Vega. She's waiting for your answer. Still the same, this one will be the basis of confirming your attendance for today. I hope that you have enjoyed our lesson and enjoy solving. Thank you very much, and you may now have your solving once more.